We know that everything in the universe has a beginning, a middle age, and an end. Even our sun. Our sun had a beginning. We know it here today as a middle-aged star, a G-type star. And we have a pretty good idea of what's going to happen in the future, maybe in 5 billion years. One of the interesting things to do is to try to go back into the early history of the sun to sort out where it came from. And several of the things that we do know for certain is that it's not a first-generation star. It has metals in it, and around it is in orbit planets, in particular the terrestrial planets that are made out of materials that could only have come from a supernova explosion. Something that I did a few years ago is I looked at the ratio of Rubidium 85 to 87 here in our solar system, and I used this to estimate how long ago a precursor star went supernova. It had to have been a supernova because of the very high mass elements that we have in our solar system. Elements past iron all the way up to uranium. This would have come from a supernova explosion. And so what I did is I played detective and was able to sort out certain very interesting things about the precursor star. Now these are hypotheses which I will share with you in this short video. But let's begin by taking a look at the sun as it is. I went through the periodic table to look for some isotopes that might be useful in trying to sort out the age to the precursor star when it went supernova. And I eventually stumbled upon rubidium. Rubidium 85 is stable. Rubidium 87 has a very long half-life, 49.76 billion years if we are to accept the results from Brookhaven National Lab. So the way that the rubidium isotopes are produced, both by the slow process and the R process, and the R process is the supernova rapid process, ideally the ratio should be between rubidium 85 and 87 should be 2.5. But what we measure today, looking at materials here in our solar system, is the ratio is 2.593. we can use that to estimate how long ago a supernova explosion occurred to produce the present ratio of rubidium. Well, first of all, let me explain the two-bucket model. Because of the way in which the isotopes are produced, we would expect 5 times more rubidium-85 to be produced, and 2 times rubidium-87, so the ratio would be 5 to 2, giving you 2.5. But because rubidium-87 decays, that ratio has changed over time. It's now 2.593. And so we can use a bit of mathematics to show how long ago the supernova explosion occurred. And it appears to have occurred 5.34 billion years ago. Here's the math. So after estimating the time back to the precursor star, the supernova, at 5.34 billion years, I asked myself is there other attributes or characteristics of the star that I can determine by the rubidium ratio. When I looked out into space and saw a correlation between the rubidium ratio and the masses of particular stars, that gave me an opportunity to try to characterize the mass of the precursor star. And it turns out the mass of the precursor star is estimated to be between 13.8 solar masses, 13.8 solar masses, could have been as high as 14.2, could have been as low as 13.3. But it's on the order of about 13.8 solar masses, which is quite exciting because if you get around 15 solar masses, your end state is not a star, your end state's a black hole. So it appears, if this is the case, that the precursor star mass was 13.8 solar masses, we just missed becoming a black hole. If it had collapsed into a black hole, it probably would have sucked up all the adjacent accreted material that it would have shot out into space. It would have been an accretion disk, and then the rest would have been history. We wouldn't be here, life on Earth and all. The other thing that I found intriguing was the question of whether there are siblings to our sun, other stars that came from the same precursor star. It is possible we might have 1 or 2 or 3 or maybe even more siblings. They don't necessarily have to be G-type stars. They could be K-type stars. They could be smaller stars. They could be dwarf stars. But the interesting thing is it might be possible to use the rubidium ratio to actually look for siblings, kind of maternity test. So there we go. My estimate to the precursor supernova 5.34 billion years ago, the mass of that star about 13.8 solar masses. And the other thing is when you actually look at an accretion model for the solar system based on simple gas dynamics, you get an estimate of about 800 million years for the accretion disk to form. There are some models that says it happened really quickly, 50 billion years. I'm a bit of a skeptic when it comes to that. But when I did a separate estimate of the accretion time and came up to 800 million years, what did I find? Well, 5.34 billion minus 800 gives us essentially what we have discovered empirically, that the age of our solar system is about 4.54, 4.56 billion years old. So it's kind of nice that the numbers seem to correlate well.